All right, chemistry, here is part 2 of your video lecture for chapter 4, section 2. In this video lecture, we're going to hit these last two objectives that we didn't get to last time. It's going to go over those again. Today, we're going to list the 4 quantum numbers and hopefully describe their significance. And we're going to relate the number of sublevels corresponding to each of the atom's main energy levels, the number of orbitals per sublevel, and the number of orbitals per main energy level. Okay? Bear with me. I'm going to have to skip through several slides to get back to where we were. All right. Atomic orbitals and quantum numbers. Quantum numbers, they specify the properties of atomic orbitals and the properties of electrons in those orbitals. Quantum numbers, they specify properties of atomic orbitals and the properties of the electrons in those orbitals. So here's the first one. There are going to be 4 of them. There are 4 quantum numbers. Here's the first one. The principal quantum number. Now, not principal like I have certain principles that I have to live by. Principal as in the person who's in charge. This is the main quantum number. It's the first one you deal with, and it gives you the most information. Symbolized by N, it indicates the main energy level occupied by the electron. Main energy level. Let's go back to Bohr's idea, simple idea of orbits. Okay? If you're on one concentric circle, you're on a particular principal quantum number. If you absorb a photon, you become excited, you want to leave your ground state, you move out one concentric circle, your N value has increased by 1. You have increased your principal quantum number by 1. You've gone from N is equal to 1 to N is equal to 2, your principal quantum number, the main energy level that you're on. The angular momentum quantum number, symbolized by L, indicates the shape of the orbital. Okay, and later in the slide show, we'll actually take a chance at looking at some of these shapes. And yes, they're going to be very convoluted and complex and confusing, but we're going to do our best. Next up, the magnetic quantum number, which is symbolized by M, indicates the orientation of an orbital around the nucleus. How is it oriented? We have several different shapes, but how we orient them in three-dimensional space around the nucleus has its own quantum number. Then lastly, the fourth one, the most recent one, the spin quantum number. And while the other 3 quantum numbers have several different possible values, the spin quantum number really only has, not really, it does only have 2 possible values, plus half or minus half. Colloquial, those are referred to as upspin or downspin. Okay, upspin or downspin. So we're talking about plus half, minus half, aka upspin, downspin. If you hear me use those interchangeably, try not to worry about it. And these indicate the 2 fundamental spin states of an electron in an orbital. And if you are interested or you've heard anything about the quantum communication of information, having information travel faster than the speed of light, that idea is harnessing the spin quantum number idea. Okay, so if you want to learn more about that concept, the spin quantum number is going to be something you want to look into to help you understand it. So let's look at some shapes. Okay, now when we're talking about shapes, which quantum number are we looking at? We're looking at L. Okay, that's the angular momentum quantum number. Okay, just going over it again. So we have s orbitals to start. The s orbital is spherically shaped. There is only 1 s orbital for each value of n. Okay, the principal quantum number. So for n equals 1, there's 1 s orbital. For n equal 2, there's 1 s orbital. As n equals 3, there's 1 s orbital. Next out, we have the p orbitals. For each of the values of n, okay, like 2 and 3 and 4, and by the way, n equals 1 is purposefully not there because when n equals 1, we don't have any L values. Okay, so there are no p orbitals when n is equal to 1. We just have the single s orbital. But for each of the values of n equals to 2, 3, 4, and onward, there are 3 p orbitals. So there'll be 1 s orbital and 3 p orbitals. They're all this dumbbell shape, but the way you're going to tell the difference between different p orbitals is how they are oriented around the nucleus. Okay, you have 3 dimensions, and so we can orient one of these dumbbells along the y-axis, one of them along the x-axis, and one of them along the z-axis. Okay, go back. The M quantum number, the magnetic quantum number, indicates the orientation. Okay, so that's what we're talking about. In 3-dimensional space, how is it oriented? And then for each of the values, n is equal to 3, 4, 5, on. And again, n is equal to 1 and 2 is purposefully left out there because when n is equal to 1 and when n is equal to 2, there are no d orbitals. But when n is equal to 3 and up, okay, anything following, there are 5 d orbitals. Now, 4 of the 5 d orbitals have pretty similar shapes, but again, they're differing in orientation. The magnetic quantum number varies. M varies for each of them. Now, 4 of them are similar in shape. We see that you can almost mistake these for p orbitals. Okay, you really could. They're not, crazy different. But each orbital has 4 bulbs, whereas the p orbital only has 2 bulbs. S orbital, I guess I'd call that 1 bulb. It's a sphere. 1 bulb, 2 bulbs, 4 bulbs. Except for the fifth d orbital here is like a donut. Okay, it is a dumbbell with a donut around the nucleus. Okay, it's pretty wacky looking. The f orbital, okay, which follows this, does exist. It is understood and well known, but it's so complex that we're not even going to bother trying to represent them visually. Next up, we are going to try to relate principal quantum numbers, sublevels, number of orbitals per sublevel, and the number of electrons possible in each sublevel. That's our last objective for this particular lecture. But this is the information that you want to know. Now, in your notes, you have 2 different charts or 2 different tables because, well, the numbers would be too small if I printed this all in one sheet. So you have 1 through 4 right here, and then 5 and 6 on the next slide. And what I'm wanting you guys to be able to do is see the patterns, okay? Pattern recognition. When n is equal to 1, there's only s orbital sublevels available, okay? There is 1 orbital per s. Okay, when we go to n equals 2, we have s and p orbitals. So how many orbitals are there? There's 1 from the s still, but the 3 from the p. So how many total? That's 4. Okay, 4 orbitals total. N is equal to 3. We have s. We have p still, but now we have d's finally. So we have the 1 s orbital, 3 p orbitals, and then 5 d orbitals. This is a total of 5 plus 3 is 8, plus 1 is 9. Okay, and on and on and on. We have one more time where we're going to add the f. Okay, these are very, very complex. We're going to add the f orbitals. There are 7 f orbitals. So now we have the 1 from the s, the 3 from the p, the 5 from the d, and the 7 from the f. That's 1 plus 3 is 4, plus 5 is 9, plus 7 is 16. So we have 16 total orbitals possible. Okay, it doesn't necessarily mean they're going to be completely full, but we have 16 total orbitals present when the principal energy level is 4, right? When n equals 4. The other thing I'd want you to be able to understand is how many electrons could potentially be housed by these orbitals. And for each orbital, you can have 2 electrons. Okay, you can have 2 electrons. Okay, so notice that we're taking each of these values. How many orbitals are there? Each value to get to this next column is being multiplied by 2. 1 times 2. 3 times 2 is 6. 5 times 2 is 10. 7 times 2 is 14. So for each orbital, okay, each individual orbital, we can house 2 electrons. So if you want to know the total number of electrons possible in an energy level in one of these n values, you simply go 2n squared. Okay, 2n squared. Or you can simply write this out. Okay, n is equal to 4. So we have s, p, d, and f orbitals. There's 1 f, there's 3 p, there's 5 d, there's 7 f's. Add all those up. Okay, this is 16. In each of those orbitals, you can have 2 electrons. 16 times 2, 32. You got it. Okay, and that pattern will hold true for all principal quantum numbers. Okay, moving on and on and on. Here is the patterns for the principal quantum number, angular momentum quantum number, magnetic quantum number, and then the names. Okay, so this is a table. We're not going to deal with this all too much. We're not really even going to deal with this too much in AP chemistry, but I do want to expose you to these things so that you can do a little pattern identification practice as we move forward.
.com.
All right, so let's talk about the atomic orbitals. So we originally had the idea that that an atom looks like a nucleus in the middle, positively charged nucleus with the electrons orbiting out around it. We're going to say that we're not going to use that model anymore. It's extremely outdated. We're going to ignore it. It's great for simplistic ideas of ideas of how an atom behaves. But now we're going to talk about we're getting more into chemistry. And we're going to talk about more in-depth things. So we're going to now use the more updated model, which is a quantum mechanical model. So Schrödinger, along with Heisenberg, came up with a new idea of what an atom looks like. It's the one we use today. Heisenberg's uncertainty principle states that it's impossible to know precisely both the velocity and locations of an electron at the same time. And he, along with Schrödinger, he kind of like calculated this huge mathematical idea of where an electron can be found, came up with this new idea of what an atom looks like. So if we go over here, we're going to actually try and describe what it is and where an electron can be located within an atom. So if you have a nucleus in the middle, and here is here's the nucleus, and back here is where the electrons are located. There are different energy levels, the principal energy levels where electron can be found. So in the principal energy level, n equals 1, n tells us n is basically which principal energy level is which. We have one orbital. We're going to call it the s orbital. And let's give an idea of what the s orbital actually looks like. If we take this balloon, it's a spherical balloon. S orbitals are spherical in shape. In the middle, we have a nucleus, and surrounding it, we have the idea of where the electron can be found. So there's one orbital for every s in s orbitals. There's only one. Looks like this. So we're going to say 1. In the n equals 2 principal energy level, there is an s also, a little bit bigger sphere. And there's also p orbitals. Okay, p orbitals look slightly different. This is what a p orbital looks like. This is 1. Even though there's 2 balloons, this is 1 p orbital. The nucleus is kind of where the nuts are, and electrons can be found either here or here, and it looks like a dumbbell shape. If there are actually 3 of these orbitals together, they come together to look like this complicated mess. So electrons can be found in anywhere the balloons are. So the nucleus is obviously in the center, and the electrons can be found here, and there are 3 of them put together to make this 3-dimensional shape. So in the n equals 2, we have 1 s orbital, and then we have 3 p orbitals. In the n equals 3, it also has s orbitals. It also has p orbitals, but it also has a d orbital. D orbitals look like flowers, a little more complicated. I didn't get a chance to make it in balloons because it's a little bit harder. But it looks like a clover. And so the nucleus is found here, and the electron can be found in any 4 of these places. Now, this is just 1 orbital. This is not 4 orbitals. This is just 1 orbital. So electron can be found here, 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 or here. So you can find there's 1 s orbital, 3 p orbitals, and 5 d orbitals. They can be oriented in different ways along the axis. The n equals 4 principal energy level. You have an s also. You have a p. Again, you have a d, and then you also have an f orbital. F orbitals are extremely complicated. Each orbital actually looks very different from each other. So I'm not even going to attempt to draw it because each one's a little bit crazy. But there's 1 s orbital. Oops, I'm sorry about that. 3 p orbitals, 5 d orbitals, and as you can guess, there are 7 f orbitals. And f is actually, for now, the highest energy orbital that you're going to find. There are theories that there are other orbitals within the principal energy level. However, we're not going to go there because it's just theoretical at this point. So as you can, if you were to put all these guys together, you'd get this insane mess-looking thing. The nucleus being here, the s orbital the 1s orbitals, the electron can be found within that, then the 3p orbitals, then the s, and then so on and so forth. So it's a lot more complicated than the Bohr's model, which is just a nucleus in the middle and the electrons surrounding it. So this is basically the atomic orbitals.
All right, let's finish up with a check for understanding. Which of the following is not described by the first 3 quantum numbers? That's the principal, angular momentum, and magnetic. It's the spin, right? So basically, which one of the 4 quantum numbers is not listed right there? The spin quantum number is the only thing not. All right, chemistry, I will see you next period.